reminder on everything for extra credit: if you don't show any work, you don't get any credit. So I want to see everything worked out as much as humanly possible. Think about all of those things we've talked about in class with presentation error and all of that information. Now, what I want you to do as I go through this extra credit is I want you to pay attention to the explanation. I mean, pretty obviously I want you to be able to do the work as well, but the explanation is really important. So the only way that you are going to get the extra credit, along with working through all of the problems that are at the end of this video, is if you listen to me and write down the letters as I say them to get the hidden message. And if you have the hidden message and then you have the work for the 5 problems at the end of the video, then you will get the extra credit. That's the only way that you're going to get it. So you do need to listen to the entire video, and I will be giving you a letter for the hidden message as we go through on each of the problems, and you need to write that down so that when you get to the last page, you can write down what the hidden message is, and then do the 5 problems and get the extra credit. So pre-calculus holiday logarithm lesson, here we go. We've got a logarithmic function, and it is the inverse of an exponential function. So when we see inverse of any function, we need to be thinking about the fact that that means that's a reflection in that line y equals x. So it says the graph shows y equals 10 to the x, which is of course the red graph that we have right here, and then its inverse, y equals the logarithm of x. And we can see how, if we put in that line y equals x, which is of course the perfect diagonal through first and third quadrant, that we would get a reflection to go through or reflect over that line y equals x right there. And so the whole gist of it is that exponents and logarithms have to work with the same properties. If they didn't, then we wouldn't be able to use those to undo each other as inverses of each other. So when we see y equals logarithm of x, we need to think that's undoing a power. More so than that, we need to realize that when it's log, we're talking about base 10. And one of the things that I had encouraged students to do last year in Algebra 2 was to use a little something that I call the snail shell method. And that's to help us translate from logarithm language into exponential form until we get a good feel for logarithms. And what you want to do is you want to make a snail shell. You're going to start at the base, which is the smaller number right after the log, and you're going to make a snail shell. And that tells you how to write that exponentially. So this will be 10 to the y equals x. Logarithms, by the way, are one of the most pure inverses that we have. They're pure inverses of exponents. The whole thing that we try to get across with inverses is that the x's become the y's and the y's become the x's. And when you look at this, hopefully you get that sense that they have actually changed roles, the x's and the y's. So as it says, the graph shows 10 to the x, y equals 10 to the x, and then y equals log of x, which would be logarithm base 10 of x. Also a quick reminder that ln is really logarithm base e. So we need to be able to translate that information back and forth. As it says, note that 0, 1, and 1, 10 are on the graph of y equals 10 to the x. And then 1, 0, and 10, 1 are on the graph of y equals the logarithm of x. Like I said, the inverses couldn't be more clear here. X to y, y to x. Recall that the graphs of inverses are reflections of each other across the line y equals x. And we can graph y equals logarithm base b of x. So not necessarily guaranteed that that is going to be a 10 or an e with different bases. But we've talked about in class how we're going to be working with natural logarithm whenever possible because that has so many special properties in calculus. But if you snail shell y equals logarithm base b of x, so let's just say for the sake of most of us being right-handed, and again, that's probably not the the best thing to do, because there are some people that are left-handed, but most of us read from left to right. So this should work no matter whether or not you're right-handed or left-handed. If we just use our properties in math and reverse those two, because they are absolutely the same whether or not it's y equals logarithm base b of x or logarithm base b of x equals y. We would snail shell that and get b to the y equals x. And again, those are going to be inverses that we have there. So when we're doing the inverses, we change the role of the x and the y. So you're going to notice here that gets flipped. And that's going to be its inverse. So now, that's how logarithms have really come to be. Logarithms about undoing those exponential powers, unknown exponential powers. And so to understand how to use logarithmic functions, we have to translate those into an exponential form. And like I said before, really the easiest and best way to do that, and I think a couple of teachers in the building will call this, a fish hook, whatever it is that you use to exponentiate those, that's what you want to get done. So in this case, by snail shelling, we would have 2 to the 4th equals 16. So we know that is a true logarithm statement right there, using that snail shell process. All right, now, reminders, since we're going to be using this pretty intensely later on in Chapter 3. The properties of exponents are the same properties that we need to use for logarithms. So when we raise any number to the 0 power, we get 1. That's just part of the definition that we have for properties of exponents. When we need to divide, we subtract. So division is subtraction in the language of exponents. When we have a negative exponent, that is for reciprocals. And we've used those properties along as we've gone through this year, as we reviewed in Chapter P, all kinds of properties of exponents. When we need to raise something to a power, as long as it is pure multiplication or pure division, inside parentheses there, we can distribute that power. Notice it's just distributing n to both the a and the b terms. When we raise a power to a power, in that case, it has to get bigger faster. And in order for that to happen, we multiply. So power to a power, we multiply. And then, of course, something we used quite a bit already this year, when we have similar bases and we need to multiply, we add the exponents. So these were all properties of exponents that we reviewed in Chapter P, and you're going to notice so many similarities between what you see in the properties of exponents and then the properties of logarithms. As we take a look at our properties of logarithms, which is for any positive numbers, m and n and b, where b is not equal to 1, the following properties apply. One of the things I really want to focus on here is that logarithms are defined for positive numbers only, and that's because the domain of our logarithms is from 0 to infinity. And we have to make sure that we remember that we can only take the logarithms of positive numbers. So when we're trying to evaluate, that's something that has to stay in the back of our mind. The product property says if you want to multiply, you really need to add. And if you think about exponents, that's exactly what we were doing right here. If we want to multiply, we add. Now, the quotient property says if you need to divide, you should be subtracting. All right? Divide, subtract. They follow those same properties. And then down here, we see that it says if you want to take your base and raise it to a power, you really need to multiply. And that follows the power to a power property. We're already talking about things that are exponential and we want to raise it to a power. Well, that's a power to a power, and that means multiplication. So notice that the power of n actually came up front and became multiplication. And those are the properties that we need to use whether we're trying to expand or condense logarithms. So let's get to it, and I'm going to tell you that for this first problem, the first part of the hidden message is L. L as in lamb. So write down an L as part of the hidden message. And it says write each expression as a single logarithm, and that would be called condensing. That is condensing. And I take a look at this and I think, okay, all I see up here right now is addition. So using those properties of exponents and properties of logarithms, I remember that addition comes from multiplication. So what I really need to do is the logarithm base 3 of 4 times y times 8x. So we'll go ahead and do that, and we'll have 4 times 8 is 32 xy. So that's the logarithm base 3, and we wouldn't necessarily need the parentheses of 32xy. So as basic as that. Now if you're looking at this and you're thinking, okay, but what about this piece right here, Cedar Home? Well, they just didn't take the time to separate it. They absolutely could have written the logarithm base 3 of 8x as logarithm base 3 of 8 plus the logarithm base 3 of x. And then we would have more addition to work with there. You know, we'd have another one that we could work with. But they didn't. We just need to be able to figure out, you know, what's going on from the problem that they initially gave us. So this would be our answer. Now the last thing that I always check is this a base that I could use to evaluate the number, the numerical part of my answer? So I start thinking about that snail shell, and it would be 3 to the something equals 32, and I realize that's not going to work out nice. If it had been base 2, yes, I could get to a 32 with that, but it wasn't. So that answer is complete. There isn't anything else that I can do with that. All right, so then number 25 here, hidden message. The letter is O. The letter is O for the hidden message for number 25. This one says expand each logarithm. So I'm looking at this problem and I'm thinking, okay, basically I need to check out any multiplication or division first because those are going to change to addition and subtraction. Well, these are being multiplied, so I need to change that to addition, but this is being divided, which means I need to change that to subtraction and separate it. So this will be the logarithm of a squared plus the logarithm of b to the third, because that was multiplication, and multiplication in logarithm language is addition. And then I need to subtract the logarithm of c to the fourth. But now I realize there's also a new wrinkle with this problem, and that is that I have powers. So I have already this exponential situation where I'm raising things to a power. A power to a power, we're supposed to multiply. So that means this 2 needs to come out in front. This 3 needs to come out in front of this term, just this term. Notice that. It was only the a term that was being squared and only the b term that was being raised to the third power. Same thing in the back. We're going to go ahead and bring that 4 ahead and show the multiplication. So 2 logarithm of a plus 3 logarithm of b minus 4 logarithm of c. And again, what I'm doing is quickly checking to make sure that there isn't anything that could be simplifiable in this case. And because we have base 10, there's no base listed. That means when we have log, that's base 10. And I have variables for the numbers that I'm trying to evaluate. I would not be able to do anything further with that. For number 27, for the hidden message, your letter is G. Your letter is G. Now, for this one, I look at this and I realize, well, they have a square root piece in here. And when we have a square root piece and we're going to expand this, we have to change that into a fraction power, a rational exponent. So I look at this first and notice, all right, wait a minute, this is really multiplication taking place here. So that's going to be addition. But I'm going to go ahead and rewrite that square root of 3a to the 5th first, and realize that that's really 3a to the 5th to the 1/2 power. And as I noted earlier, when we do have pure multiplication in the parentheses, we can go ahead and distribute that. So that'll be 3a to the 1/5 and a to the 5/2. So that makes this easier for us to separate as we are trying to expand this logarithm. So now I see, all right, lots of multiplication taking place here. That's going to be addition. Logarithm base 8 of 8 plus logarithm base 8 of 3 to the 1/2 plus logarithm of a to the 5/2. And I realize, not done. I have powers being raised to a power here. Remember, we're talking about exponential situations that we're raising to a power. So this one I'll leave alone, but I need to bring those exponents out in front of each of these terms to change those powers into multiplication, raising a power to a power. Oh, forgot my little 8 here on this one. All right, now, last thing to do again is to check and see, is there anything here that we could simplify? Well, this we absolutely can. Think about making your snail shell. Let's just say equals x here, and we snail shell this and we would say 8 to the x equals 8. Well, that's 1. So we're going to rewrite logarithm base 8 of 8 as 1 plus 1/2 logarithm base 8. And as I'm writing this one down, I'm thinking 8 to the something is 3. No-ish, that's not going to work out nicely. You know, I'm not going to simplify that. And this last one, of course, has a variable. So there's nothing we can do there. So what do you need to notice that was pretty specific to this problem? And that is that our expanded form has fraction powers. So when these are expanded, we use those rational exponents. So expanded fractions for powers, for exponents. And when it is in condensed form, that's when we use roots. So important to notice that piece, that when it's condensed, we're going to use roots. And when it's expanded, we're going to use fractions for exponents. Basically, you can think of it as this. If it starts off with roots, you're going to need fractions when you get done. And if it starts off with fractions, in the case of them giving us the final answer here and asking us to condense it, then we have to change that back to roots. So whatever you have, go the opposite way when you're working with it. All right, so hidden message so far, LOG. For number 57, the hidden message letter is S, as in snake. S, as in snake. All right, this one says write each logarithmic expression as a single logarithm. And I kind of think order of operations when I'm looking at this. I have parentheses here. So I need to deal with that first. And since I have a fraction power out in front, that's really going to be taking the square root. But for now, what I'm going to do is go ahead and put that fraction power back up where it came from. Now notice, I'm not going to mess with that last term because that was not in the parentheses. That was not raised to that 1/2 power. Now I'm going to go ahead and change that to square root. And hopefully as you're writing that down, you're realizing, oh, wait a minute, we know what the square root of 4 is. I'm going to go ahead and put this 3 back up for a power while I'm here as well. And just get everything back to the powers where it came from. So now, as I look at this first one, I realize, well, that's logarithm base x of 2 plus logarithm base x of the square root of y minus logarithm base x of z to the third. And remember, this one was a single logarithm, which of course is condensed. And we're going to do that a lot whenever we have to solve. So what we need to do now is recognize that addition is multiplication. So this is logarithm base x of 2 times the square root of y, so 2 square roots of y. But then subtraction is division. And again, at the end, what I'll usually do is take a peek and say, is there anything in that fraction that I could go ahead and simplify? There isn't in this case. There's nothing that we could simplify for number 57. Number 58, I'm not going to give you a letter for this one. For this one, for the hidden message, we're just going to ignore that piece. And then for 58, if we want this as a single logarithm, what we have to do is get those powers back up where they belong. So this will be the logarithm base 4 of m to the x plus logarithm base 4 of n to the 1 over y minus logarithm base 4 of p. Now, interesting situation here is that n to the 1 over y. So I think, well, what is 1 over y? Well, that's y to the negative 1, and there's a whole lot of ways that we could deal with that. What I'm going to do, though, is think, okay, this came with the fraction that we had. What I need to have if I'm going to condense this is roots. So I'm going to write this as logarithm base 4 of m to the x plus logarithm base 4, because the 1 over y, remember, if it's 1/2, it's the square root. If it's 1/4, it's the 4th root. If it's 1/5, it's the 5th root. That's really the y root of n. All right, and now I realize that what I have left here is just addition, which is multiplication, and subtraction, which is division. So this will be the logarithm base 4 of m to the x, y roots of 9 over p. They all had that base of 4, and since that base was the same, we could go ahead and condense that really nicely. So that's number 58. For number 63, you're going to give me another letter for the hidden message. For number 63, the letter is A, as in apple. A, as in apple. This one is expanding the logarithms. And as you look at this one, I'm hoping that some of you are going to say, wait a minute, they didn't simplify that one first, because we know that that's going to be reciprocals, that P should really go up on top. And then it should really look like that. You absolutely could do that right away. I'm going to say maybe somebody doesn't notice that. Maybe you don't notice that right away. So let's see what happens with this problem if you don't notice that right away. So if you didn't notice it, you would say, well, it's logarithm of m to the 3rd, and then minus logarithm of n to the 4th, plus logarithm of p to the negative 2. Now these all happen to be base 10 logarithms, so I don't need to bother writing bases down. And then, well, with the parentheses, we should really distribute the negative. And now we realize, well, we should be putting those powers out in front, because when you're raising an exponential to a power, that's a power to a power, which is multiply. So we put those out in front of each of the terms, and we get to this last one, and we see there's a little weirdness going on, because we have subtraction out in front, and if we bring that negative 2 down in front, it's going to say minus a negative. Oops, forgot the 2. So minus a negative would be a plus, and it would look like so. And we have the powers gone, and now this is just a situation where we have subtraction and we have addition. So you're thinking, gosh, is this right? Well, this is division. So we'd have the m to the 3rd over n to the 4th, which we do. And then this is addition, which is going to be multiplication again. So that would be multiplication to the numerator, which really does have that in its simplified form. So whether or not you notice that right away, that this negative 2 power should go to the numerator, or you don't, and you just go ahead and do the math for logarithms, you will get to the same expansion. It won't make any difference, which is really nice. All right, for number 67, let's see, we have R for Ralph. So 67 is R as in the name Ralph. All right, 67 is an interesting problem. Let's take a look at this. Because we have that square root, we need to think of this, and again, this is base 10, as x squared minus 4 to the 1/2 over x plus 3 squared. Now, if we had an x plus 3 in the numerator and an x plus 3 in the denominator, at this point we could do something. We could make a change here, but we don't. And what you should be thinking is x squared to the x squared minus 4, is that a perfect square root? If I actually took the square root of that, would that work? And the answer is no. But hopefully you're thinking in advance, wait a second, isn't that really x plus 2 and x minus 2 being raised to the 1/2? Exactly. That is exactly what you have to think, because we know that needs to be separated. Now what this means to us is that both of those pieces need that 1/2 power. So it will be the logarithm of x plus 2 to the 1/2, x minus 2 to the 1/2, and we can do that because we have multiplication here. Remember, we have parentheses telling us this is multiplication, over x plus 3 squared. And now we would separate this into multiplication and division, and multiplication is addition in logarithm language. So the logarithm of x plus 2 to the 1/2 plus the logarithm of x minus 2 to the 1/2, and then of course we're only dividing by the x plus 3 squared in our denominator. And now our job would be to put those fraction powers out in front as multiplication, because with a power to a power you multiply. So 1/2 log of x plus 2 plus 1/2 log of x minus 2 minus 2 log of x plus 3. And in this case, because we were working with so many variables, there isn't anything we're going to be able to simplify as we go through that one. So that one hidden message letter was R as in Ralph. For number 78 on the next page, the hidden message letter is E. E as in elephant. All right, next one up. Says simplify each expression. And so for 78, I notice this is already expanded. What they're really asking me to do is condense this. And it's quite the monster. So I notice we have subtraction and then we have addition. So that means we're really doing division and then multiplication. So this will be logarithm base 3 of x plus 1 over 3x squared minus 3x minus 6. And hopefully while writing that down you think, wait a minute, a 3 will come out all of those. And then we need to add, which means multiply. And remember, x minus 2 is the same thing as x minus 2 over 1. So really, we are just multiplying that x minus 2 in our numerator. Now, my hope would be that something's factorable here. So I go ahead and leave my numerator exactly as it is. But in my denominator, I pull out a 3. And then I check that out to see, is there anything that I can do to factor my x squared minus x minus 2. So we know x times x will give us the x squared. We just need two numbers that multiply to -2 and add to -1, and that's going to be -2 and plus 1. So that gives us some really great canceling that we can do here. And that gives us logarithm base 3 of 1/3. Now, seeing those 3's, you should immediately think, wait a minute, I think I can evaluate this. I can actually get a one number answer here. 3 to the, think of that as an x, 3 to the something equals 1/3. Well, that's the reciprocal. And so for the reciprocal to happen, that had to be a -1 power. This is the awesomeness of math. This says -1. That is just so cool. We have our own little secret code system in math for ways of writing things, and that is just fantastic. All right, this one says, what is the solution of 15 to the 3x equals 285? And our mystery letter here for our hidden message is A, as in apple. A as in apple. So 15 to the 3x equals 285 poses a problem. The problem is that our x value is actually part of the exponent. That means I need to get rid of that 15 somehow. And from last year, what we would have done was take the logarithm base 15. But now we know that as we're going to calculus, we really should be using natural logarithm whenever possible. So we're going to take the natural logarithm of both sides, and then we're going to see what happens. Well, now I notice I have a logarithm that has a power, and that power needs to come out front as multiplication. Now, I know this looks really strange, but what you need to remember is this is a number. Your calculator holds it for us. That's a number in your calculator. This is a number in your calculator. And everything going on the left-hand side over there is multiplication. So to get rid of that, we're going to go ahead and divide, and we are just dividing by a number. So over here, these are going to cancel out. And this is a situation where if we needed to, we could just punch that in and get the answer right now. But we want to avoid any kind of rounding error. So instead, we think, okay, I don't have x by itself. Normally, I would divide by 3, but I've got a fraction on the other side. So you know what I think I'm going to do? I'm going to multiply both sides by 1/3. And then that will give me the natural log of 285 divided by 3, natural log of 15. Now, you could certainly just punch this in at one time, but you're going to have to be very careful about your parentheses. The calculator doesn't know that it needs to do order of operations for fractions, which means everything in the top gets done first, everything in the bottom then gets done, and then you do the division. Or you could punch in the natural log of 285 divided by the natural log of 15, get an answer, and divide that by 3, or multiply it by 1/3, whichever way you want to do that. But in the end, this is going to work out to 0.6958. And you might say, well, Cedar Home, we're supposed to go 3 decimal places. Yes, we will in class, but generally for logarithms, you go to the 10,000th position. So for this video, I'm going to go ahead and stick with the 10,000th position. Then, for 2a, the hidden message letter is W, as in whale. W as in whale. So we need the solution 5 to the 2x equals 130. And again, we're going to focus on the fact that we want to get used to using natural log. So we'll take the natural log of both sides. And we have the 2x, which needs to come out in front and become multiplication. So the next thing we would do, just like in the last problem, is divide both sides by the natural log of 5. You might be wondering why I'm doing 2 of these, but this is really a very large concept for what we're going to do later on in this chapter. So now these are going to cancel out, and we get 2x equals the natural log of 130 divided by the natural log of 5. And again, you can think of it as dividing by 2, but dividing by 2 for a fraction would be multiplying by the reciprocal. So we could multiply both sides by 1/2, and that would give us the natural log of 130 over 2 natural log of 5. And of course, when we do punch this in the calculator, we do so very carefully. Or you can punch it in as natural log of 130 divided by natural log of 5, and then divide by 2. And this is approximately 1.5122, which reminds me I should use approximately up here as well, because these were rounded answers that we gave here. All right, so we're solving. We're using natural logarithms, and we are solving. And then we get to this one, which is what is the solution of log quantity 4x minus 3 equals 2, and our hidden message letter is E. E as in everywhere, E. And it already has a logarithm in it. It has log. Well, what you have to remember is that's log base 10. And whenever we're in a situation where we have logarithms that we need to solve, we want a snail shell so we can get an answer. So to get rid of that logarithm piece, we have to exponentiate, which means we're going to take 10 squared and set that equal to 4x minus 3. Well, that's 100. So we would add 3, and we would divide by 4. Then we plop that into our calculator and hope for something nice, and it is something nice. It is 25.75, exactly. So when you have logarithms, you want to have them condensed into a single logarithm so that you can just snail shell and solve. And that's the importance of that problem as we get to this next one, which is what is the solution of the logarithm of the quantity x minus 3 plus logarithm of x equals 1. And the hidden message letter for this one is S. S as in salmon. S. I need this condensed. Well, this is addition. Addition in logarithm language is multiplication. So I notice that's a little awkward, so I'm going to go ahead and distribute that x, like so. And then change my thinking to, okay, solve. I have to solve this. Well, to solve this, we remember the base is a 10 and we snail shell it. So 10 to the first equals x squared minus 3x. Well, that's a quadratic. That should have two solutions. So I'm going to go ahead and hope that this might be factorable and move everything over to one side and take a peek at it. If it's not factorable, we could always use completing the square, we could use the quadratic formula, whatever we need to use here. But we need two numbers that multiply to negative 10 and add to negative 3. The good news is we have a couple of those, negative 5 and positive 2. So that means our solutions are 5 and negative 2. But as we were going through this problem, we exponentiated. We raised something to a power. And when that happens, we have to double check that we are going to get solutions that work. We have to check our answers and make sure this is going to work. Now, a 5 up here would be the logarithm of 2 plus the logarithm of 5 equals 1. And yeah, we should probably go through and check the whole thing, because what we're going to do is just punch that into a calculator. So log of 2 plus log of 5 equals 1. You can punch that in. You'll see that that one works. But if I put negative 2 into these two positions, I'm evaluating the logarithm of negative numbers. And we cannot do that. That is not in its domain. So this one is extraneous. Remember, we do not evaluate the logarithms of negative numbers. Now we're going to go on to still some solving. But on this page, we're going to deal a little bit more with E and with our natural logarithms. Not in 73, but a little bit later on here. So this says solve each equation, if necessary, round to the nearest 10,000. Hidden message letter is O, as in ostrich, for number 73. O as in ostrich. So in order to solve, we need this condensed. Well, I'm going to go ahead and put that power of 2 back up where it belongs first, before I go ahead and do that multiplication, because notice now we have logarithm statements of the 4 and the x squared that we can deal with. And that with addition is just multiplication. So logarithm of 4x squared equals 6. We get to this point and we think, well, it has logarithms. Well, we talked about this earlier. If you want to solve a logarithm statement, write that base in there and snail shell. So this will be 10 to the 6th equals 4x squared. 1, 2, 3, 4, 5, 6 zeros there. We would divide by 4. And then we would take the square root, which would give us plus or minus 500. But as we just talked about, we know that that negative 500 in this position would be extraneous. So we would have positive 500 for our answer for number 73. So now, more into the natural logs and E, which is what we really were going to be using a lot in calculus. So what is 2 natural log of 15 minus natural log of 75 written as a single natural logarithm? Well, I notice I need to put that power back up here, so that'll be the natural log of 15 squared minus the natural log of 75. And then there's this subtraction here, which is division. So natural log of 15 squared over 75. Well, that's the natural log of 225 over 75. And that's just the natural log of 3. So again, just writing things a little different manner. We're really just manipulating here. there. So the natural log of 3 is the exact same thing as 2 natural log of 15 minus natural log of 75, but obviously natural log of 3 is much easier to work with. So those are the types of things we want to focus on. And our hidden letter for this one was M, as in Mary, M as in Mary for this one. The next one doesn't get a hidden letter. This one is, what are the solutions of natural log of the quantity x minus 3 squared equals 4? And for this one, we have that natural log in there, and we're kind of wondering, how do you get rid of that? Well, that's logarithm base e. So then this problem really is very similar to two problems ago, where it just said solve each equation, if necessary, round to the nearest 10,000. We're going to snail shell this. So e to the 4th equals x minus 3, the quantity squared. And we would want to go ahead and take the square root of both sides of this to make this easier to solve. And that would give us a plus or minus e squared. Well, then we'd add 3 to both sides. And we would grab a calculator and see what we get for our answers. So if we do the addition, 3 plus e squared, we get 10.3891. And if we do the subtraction, negative 4.3891. And we immediately want to cross off that negative 4.3891 because we say, aha, we cannot take the logarithm of negatives, except, look what happens here. Whatever we put into this equation will be squared before it is evaluated. And that means whether or not we put a positive or a negative in for our answers, we will be able to evaluate this. So both of these solutions actually come out good, because this time we're dealing with a quadratic in there and we're squaring it. By the way, in the future, if we get to this point and we can't just take the square root and get this to work out nicely, we will in some cases be having to expand and move everything over to one side and then figure out how to use the quadratic formula or completing the square with e involved. Even go so far as maybe try to factor with e in part of our solution. So that was what are the solutions of the quantity x minus 3 squared equals 4. And then part of the hidden message for what is the solution of 4e to the 2x plus 2 equals 16, the letter E as in everybody. So E is the hidden letter for what is the solution of 4e to the 2x plus 2 equals 16. Now, your algebra skills and your intuition should kick in, and you should say, wait a minute, I've got to subtract that too. Absolutely have to subtract that too. Wait a minute, got to get rid of that 4. Absolutely. Divide by 4 and reduce and get 7/2. Ooh, how do I get rid of e? Well, that's what natural logarithm is for. Remember, that's the inverse operation. The logarithm with the same base. So logarithm base e of e, those are inverses of each other. And that's going to be natural logarithm. So we teach the natural logarithm of both sides. And what's going to happen is we'll bring this 2x out in front, because that was a power. And those two are going to drop out because they're inverses. So we get 2x equals the natural log of 7/2. So we could go ahead and either multiply both sides by 1/2 or divide both sides by 2, but we're going to put this in the calculator anyway. So I'm going to go ahead and maybe write this a little more attractive than division here. So 1/2 natural log of 7/2. And we would go ahead and punch that into the calculator, and 0.6264 is what we would obtain, of course, with rounded answers to 10,000ths, because we were just working with logarithms in this section. We weren't going any farther with that. A reminder again, we go to the 3 decimal places, the thousandths, in pre-calculus, but pretty obviously when we were working with logarithms last year, and when you are working with logarithms with math at the college level, sometimes you will go ahead and do 10,000ths, because that really is the understood way to do logarithms. So here we are at the end, and here's the extra credit assignment. The first thing you're going to do is go back and find all of those letters that you wrote down for the hidden message and come up with a little phrase to tell me that you actually watched the video. And then we have the following problems and a reminder. No work, no credit. I want every little step as you go through these things. If you're thinking, Cedar Home, normally I'd do these 2 steps at once. Don't, because you probably will not get the credit for it. I want to see that you understand each and every step of this problem. So it's not just about getting the right answers. It is also about showing me that you remember those properties of exponents that are the properties of logarithms as you go through here. So for 1 and 2, you're going to expand those logarithms. Again, of course, you can see that those are already condensed. So think about what I did in the videos to go ahead and go through that process. And then for number 3, you're solving that equation. And like it says, if necessary, you're going to round to the nearest 10,000th. We'll stick with those 4 decimal places. And then number 4, solve the equation, check your answers. I'm going to scoot this up just a little bit so that you have all of these in one window here. And we've got some solving with natural logarithm in number 4. And then number 5, use natural logarithms to solve each equation. So hidden message and 5 problems for you to work through step by step. I'm going to leave that up here, and I really hope you are enjoying your holiday season.